Very good morning, students. Today we'll discuss about chapter 10, temperature distribution in solids and in laminar flow. In this chapter we will discuss about some heat conduction problems which are similar to the viscous flow problem that we discussed in chapter 3. So in this chapter we are going to discuss about the cell energy balance, boundary conditions, heat conduction in a different systems like a electrical heat source or viscous heat source, and then finally we'll discuss about the heat loss through the cooling film. Before starting the various derivations related to the heat conduction, first of all we'll discuss about the how to write the cell energy balance. In a similar way we discuss about the cell momentum balance in chapter 3. Similarly, we can write the cell energy balance over the any system at steady state. The first term which will include into the cell energy balance is rate of energy in by convective transport minus rate of energy out by convective transport. Means convective transport is because of the flow and molecular transport is at the molecular level. So rate of energy in and out by convective transport and a rate of energy in and out by molecular transport. So these will be the four terms which will include into the cell energy balance, except that you can write the terms for the work done. So a rate of work done on the system by molecular transport minus a rate of work done by the system by molecular transport. So rate of work done on the system is taken positive and rate of work done by the system is taken to be negative. Except that there will be a rate of work done on the system because of the external forces that you have to consider. And finally, the rate of energy production. So these will be the term you have to add and subtract these terms, which equal to 0 will be nothing but equal to the cell energy balance. Now this energy balance production, the last term included into a cell energy balance, what it includes? That energy get produced or heat get produced because of the degradation of electrical energy. Heat is also produced by friction, that is viscous dissipation, and also the heat is produced during the chemical reaction. So if the reaction is exothermic, then the heat will be get produced because of the chemical reaction. So before solving the various derivations, we will understand what is the procedure to solve the heat conduction problems. So first of all, again you have to select the thin element or the cell which is perpendicular to the direction of the heat flow. Write down the energy balance equation over the thin element. Then consider the definition of first order differential equation for heat fluxes and put it delta x tends to 0. You will get the definition for first order. Then write the Fourier law of heat conduction and integrate these various equations. You will get the two different integration constant for the two integrations. Then you can find out that values by applying the suitable boundary conditions. Finally, find out the temperature distribution profile, maximum temperature, average temperature and heat flow. So this will be the approach for the derivations that we will discuss in this chapter. What will be the boundary conditions that is used to solve the unsteady state energy balance problems? The first will be you have to define the temperature at the specific surface. You have to define the heat flux which is normal to the surface. At the interface, okay, the continuity of temperature and heat flux is normal to the interface. That is required. And at the solid fluid interface, the normal heat flux is given by Q is equal to H into T naught minus Tb. This is called as a Newton's law of cooling, which also defines the term called as a heat transfer coefficient. So H is called as a heat transfer coefficient. Now The very important derivation from this chapter is heat conduction with electrical heat source. So earlier we discussed electrical heat source, viscous heat source and nuclear heat source. So this electrical heat source derivation is very important. So what you have to consider in this, you have to consider a small electric wire. Have you seen the electric wire? It looks like a circular cross section having a radius r and electrical conductivity of Ke. See, this electrical conductivity is different Ke, which having a unit of 1 upon ohm into centimeters. This wire which carries a electric current with a current density capital I, that I is in ampere per centimeter square. Now this transmission of electric current, it is an irreversible process. You know, transmission of electric current through the wire is a irreversible process. Some of the electrical energy is get converted into the thermal energy. This electric wire of circular cross section of radius r and length is shown in the figure. So this is nothing but the diagram where you have to apply the energy balance. So this is electric wire of radius capital R, length L, and the heat produced is by the electric heating. So this is QR at R, this is QR at R plus delta R. The radius of the thin element is a small r, the thickness of the thin element is delta R, and we are going to apply the unsteady state balance. Before that, we'll find out what is the rate of heat production per unit volume. So this is equation gives you the rate of heat production in watt per volume in centimeter square. So SE is equal to rate of heat production per unit volume is equal to I square by Ke. SE is heat source in watt per centimeter cube, I is the electric current in ampere, and Ke is electric conductivity in ohm inverse centimeter inverse. Now assume that the temperature rise in wire is not so large and the temperature dependence on either thermal or electrical conductivity needs to be considered. The surface of the wire is maintained at temperature of T0. For energy balance, we will select the system as a cylindrical cell of thickness delta R and length L, and various terms of the overall energy balance will be shown. So this dotted line will be nothing but the thin element cross section on which we are going to apply the energy balance. What will be the rate of thermal energy in across the cylindrical surface at R? So rate of thermal energy in across cylindrical surface. So it will be obviously along the circumference. So it will be 2 pi RL will be the nothing but unit will be meter square into QR heat flux watt per meter square. So meter square get cancelled, it will be a watt. So 2 pi RL into QR. What will be the thermal energy out across the cylindrical surface at R plus delta R? It will be 2 pi R plus delta R L into QR at R plus delta R. So it will be similar, only there will be R here, there will be R plus delta R. The rate of heat production already we seen it is SE. Its unit is watt per centimeter cube. So you have to multiply by volume. So volume will be 2 pi RL circumference into delta R. Thickness will be the volume. Volume into SE, rate of heat production. So we can write overall energy balance for this system is 2 pi R delta 2 pi R L QR at R minus 2 pi R delta R plus R plus delta R L into QR plus 2 pi R delta R L into SE. So what you can do is you can divide this equation by 2 pi delta R into L. What will be the equation becomes? If you will get this equation, this is R QR at R plus delta R minus R QR at R upon delta R, limit delta R tends to 0 is equal to SE into small r. So you solve this equation, you will get this limit delta tends to 0 on this equation. And as we know, this above equation 10.5 will be the definition of d by dr of rqr, n is equal to se into r. Now you have to integrate this equation and you have to find out value of qr. So you will get value of qr is equal to se into r by 2 plus c1 by r. So first integration constant is introduced. You have to write the first boundary condition. What will be the boundary condition? Boundary condition will be at r is equal to 0, qr is not infinity. So qr having some value. So then c1 becomes equal to 0. Put c1 is equal to 0 in above equation. qr becomes is equal to se into r by 2, where r is a heat flux in r direction. So what this equation 10.9 suggests? It suggests that the heat flux increases with increase in a radius. So as radius goes on increasing, the heat flux goes on increasing. Now here we can substitute the Fourier law of heat conduction. Qr is equal to minus k into dt by dr, and you can compare both equations and you can write minus k into dt by dr is equal to se into r by 2. Now rearrange the terms and take an integration of this equation. You will get the equation T is equal to minus Se into R square by 4K plus C2. And thus you introduce the second integration constant. Again you have to put the second boundary condition and you have to find out value of C2. What will be the second boundary condition? Second boundary condition will be is at R is equal to capital R. What will be the temperature? Temperature will be T is equal to T naught. That already we have considered. So putting this condition, we can find out value of C2, that is it becomes equal to T naught plus C into R square by 4K. Put this value of C2 again in the equation of temperature. You will get this equation. By solving this equation, you will get equation for temperature difference T minus T naught is equal to Se into R square by 4K bracket 1 minus R by capital R bracket square. So this is how you will get a temperature difference between a temperature at any distance r to the surface temperature. So this equation represents the temperature rise is a parabolic function of the distance. Now if you want to find out the maximum temperature rise, what you can find out? You can find out T is equal to T max when it is possible at r is equal to 0. Put T max minus T naught, you will get the value of equation T max, which is equal to T plus Se into R square by 4K. Now average temperature rise is find out by integrating second integration of T minus T naught. So how you can write the average temperature rise is average temperature T minus T naught is equal to 0 to 2 pi integration 0 to R integration T minus T naught into R. See here, what will be the cylindrical coordinates? Instead of dx dy, you can write dr into d theta upon 0 to 2 pi integration 0 to r integration r into dr d theta. Okay. Now you have to solve the first integration with respect to dr. You have to solve the second integration with respect to the d theta. Simultaneously solve the denominator and you will finally got the equation of T average minus T naught is equal to Se into R square by 8K. So earlier you find out T minus T naught. Here Se into R square by 4K into bracket 1 minus R by capital R bracket square. And here you find out T minus T average minus T naught is equal to Se into R square by 4K. Where T naught is a surface temperature, Se is a heat source and R is a radius of the wire. Now what will be the heat flow at the wall surface? How it is to find out? It is find out by knowing the value of QR at R is equal to R into circumference 2 pi RL. So multiplying by 2 pi RL into QR will give you the rate of heat flow, that is equal to QR at R is equal to pi R square L into SE. This is how you can find out the maximum temperature, average temperature and heat flow through an electric wire. The next derivation is heat conduction with a nuclear heat source. But this derivation requires a lot of assumptions and is also out of syllabus. Next is heat conduction with a viscous heat source. Okay, you can derive this equation and you can find out the value for temperature difference again, and you can find out this T minus T naught by TB minus T naught. Generally the problems are asked based upon this maximum temperature to the T naught, this temperature. So you are supposed to know this equation of T minus T naught is equal to 1 half mu V B square by K x by B bracket 1 minus x by B plus x by B. So you can solve this derivation. Heat conduction with electric heat source. Again, this derivation also requires a lot of assumptions, so this will be also beyond the syllabus. So only the important derivation is electric heat source and viscous heat source. This composite cylinder, this also is not right now in a syllabus. So only you keep in mind the final equation. So if any problem is asked, you can solve that. Heat conduction through the composite cylinder, this is also in out of syllabus. So only the part that remaining is heat of conduction through the cooling film, that we will discuss in the next lecture. Thank you.